So before we get started, I want to give you a heads up. This talk is a little bit longer than I intended it to be when I first started drafting. It's really hard to stuff all of the things I wanted to say into a 25-minute slot, but thanks to Matt and Jameson, I think I'm still gonna be able to get you out to lunch on time. So with that out of the way, hi, I'm Lynn Clark and I make code cartoons. And I also work in emerging technologies at Mozilla. So that's things like the Rust programming language and an experimental browser engine called Surfo that's super fast, and WebAssembly, and that's what I'm going to be talking about today. If you look at the schedule, this is the official title of the talk. So this is what I originally submitted this talk with. But as I started preparing the talk, I felt like I really wanted to change this title. Now I thought of changing it to this, what WebAssembly could potentially mean for React, but instead I decided to go with this. And I really like this one because it's reminiscent of a whiteboard, and that's the kind of talk that I'm going to be giving today. I'm going to be sketching out ideas for how WebAssembly could be used in React. But these are just a few of many ideas. So the future of WebAssembly in React might look quite different from this. I've been able to talk about these ideas. I've been very lucky that I've been able to talk about these ideas with a number of people, both inside and outside of the React community. And in particular was my conversations with a couple of people that informed the content for this talk. So those people are Luke Wagner, who was one of the folks who came up with ASM.js, which was a precursor to WebAssembly. And he also did a lot of the work to push WebAssembly forward. And Sebastian Markbridge, who of course is on the React core team and has done a lot of the work pushing the fiber reconciler forward. So this talk doesn't just reflect my own ideas, but also the insights of a number of other people. Now I'm going to start the talk by looking at how WebAssembly could be incorporated into React today in a pretty straightforward way. And I'll explore the impact that that could have. And then I'll look into the future. And I'll look at what changes are coming in WebAssembly and what changes you might see in the React tooling ecosystem. And I'll see how those could come together to create some other interesting possibilities. Before I get into any of that, though, I'm going to explain a little bit about what WebAssembly is. Now, I just gave a whole talk about this at JSConf EU a couple months ago, so if you really want to know more, I'd say watch that one. But to summarize, up until this point, if you were developing a web page and you wanted to do something like change the DOM in response to a click, or if you wanted to run a calculation, you'd have to use JavaScript to do it. But now with WebAssembly, it's possible, it will be possible to do these things in other programming languages as well. This presents a couple of possible benefits for React. So one is code reuse. You could rewrite React's reconciler in a language like C, and then you could reuse it in projects like React Native, where it could be compiled down directly to native code and possibly run faster on the native platform. Another possible benefit is that it could make React applications run faster in the browser, because WebAssembly can, under certain circumstances, run faster than JavaScript. So those are the potential benefits. Now let's look at the different parts of React and see which parts might be able to, we could possibly convert to WebAssembly today. So the different parts are the core reconciler, and that's the part that figures out what the changes are from the previous version of an app and the next version. And then there's the renderer, which pushes those changes out to the user interface, whatever that may be. And then React also has some additional code in it, things like the event delegation system. And finally, there is the code that you all put into the React app, things like components. So at the moment, there are parts of this code that are easier to convert to WebAssembly than others. And that's because the WebAssembly that's in the browser, so the one that shipped on by default in Firefox and Chrome in March, and that is in preview versions of Edge and Safari today, is just a minimum viable product. So it doesn't yet have all of the features that it will eventually have. One of the features that's still missing from WebAssembly is direct access to the DOM. And that means that WebAssembly right now, you can't call DOM methods or interact with JavaScript objects directly. And I'll explain more about what that means later, but because of this, it's going to be harder to code things like renderers or the event system in WebAssembly at the moment. Another option for converting to WebAssembly could be the developer's components. If we wanted those to be in WebAssembly, developers would need to be writing those components in languages that compile to WebAssembly. And right now, that's languages like C and C++. Now, React application developers probably don't want to be coding in those languages. So that's not a great candidate for now either. That leaves the reconciler, which is actually a pretty good place to start. Like I mentioned before, this opens up some possible code reuse. So let's walk through it and see what it would look like if we rewrote the reconciler in something that compiles to WebAssembly. When the user loads the page, it would start in the same way. They would download React.js, because you still need JS in order to boot these WebAssembly modules, and in addition, a .wasm file would be fetched. That contains the WebAssembly code, which is a binary. So we'll need to load the code that's in both of these files. And first we'll load the JavaScript, which will create the JS React object. And that's then going to create the instance of a WebAssembly module, which is our reconciler. To do that, it will call webassembly.instantiate. So let's take a closer look at what this does. The first thing that we pass into this is going to be the binary code that we got in that .wasm file. So that's the module code. And we extract that binary into a buffer and then pass it in. The engine is going to start compiling it down to something that's specific to the machine that that browser is running on. So Mac, Windows. And this is going to happen off of the main thread. I've talked before about how the main thread is like a full stack developer because it handles JavaScript, the DOM, and layout. And one of the neat things about WebAssembly is that it doesn't actually need to use up any of the main thread's time doing this compilation. It can do the compilation off of the main thread. So what webassembly.instantiate will return is a promise. And this lets the main thread get back to its other work. Because it knows that once the compiler is finished compiling the module, it will be notified by the promise, which will give it the instance of this module. But the module is not the only part of the instance. I think of the module as kind of like an instruction book. And the instance is like a person who's trying to make something using that instruction book. But in order to make something, they're going to need raw materials. They're going to need things that they can work with. And this is where the second parameter to WebAssembly instantiate comes in. That's the imports object. I think of the imports object as kind of like a box of raw materials that the instance is going to use so that it can follow these instructions to make something. And that imports object can have 4 different kinds of imports. So it can have values, which are basically global variables. And the only types that WebAssembly really understands at this point are integers and floats. So they have to be one of those two, but that's going to change as we add more types to WebAssembly. It can also have function closures, and that means that you can pass JavaScript functions, which WebAssembly can then call. And this is particularly useful because, as I mentioned before, WebAssembly doesn't have direct access to the DOM, so what you can do is set up a JavaScript function that makes the changes that you need to the DOM, and then WebAssembly can just call that. Another kind of import is memory. And this concept of the memory object confuses a lot of people, so I want to go into this one a little bit more deeply. First, I'm going to give you a little crash course in how memory is handled in different programming languages, and then I'm going to explain why we have this memory object for the WebAssembly module instance. So you can think of memory in a machine kind of like a bunch of boxes. And I think of these like the mailboxes that you have in an office or like the cubbies that kids have in kindergarten, because it makes it so that you can pass things to other people. So if you're in kindergarten, you could put something in a box and then tell another kid where they can find the thing that you left for them. Now, next to each one of these boxes, you have a number, and that's the memory address. So that's what you can tell the other kid, go to box 14, I left something there for you. Each one of these boxes is the same size and can hold a certain amount of info. And that size is called the word size, and it's specific to the machine. So it's usually something like 32 bits or 64 bits, but to make it easier to show you, I'm going to use a word size of 8 bits. So if we want to put the number 2 in one of these boxes, we could do it. Numbers are easy to represent in binary. What if we want something that's not a number, though, like the letter H? We need a way to represent that as a number, and that's why we have encodings, things like UTF-8. And we're going to need something to turn that letter into that number, like an encoder ring. And then it makes it easy to store that. When we want to get that back out, we're going to have to put it through something else, like a decoder ring, to get back to that letter H. Now, when you're working in JavaScript, you don't actually need to think about this memory. It's abstracted away from you. And this means that you don't need to touch memory directly. Instead, the JS engine acts as an intermediary. It manages this memory for you. So let's say some JS code like React wants to create a variable. What the JS engine does is it runs that value through an encoder to get to that binary representation, and then it finds space in the memory that I can put that binary representation into. This process is called allocating memory. And then the engine is going to keep track of this memory that is allocated for you. It's going to keep track of whether or not that variable is still accessible from anywhere in the program. And if it can no longer be reached, that memory is going to be reclaimed so that the JS engine can put new values there. This process of washing the variables and clearing it out when the variable can't be reached anymore is called garbage collection. Languages like JavaScript, where the code doesn't deal with memory directly, is called a memory managed language. This automatic memory management has some advantages. It makes things easier for developers, but it also adds some overhead. And that overhead can sometimes make performance unpredictable. Now, WebAssembly is different. It doesn't offer that layer of abstraction. Instead, you're operating directly on memory. And WebAssembly only gives you two operations. You can load and you can store. And when you're doing this, you're working with one memory address at a time. If you're writing in a higher level language like C or C++ that compiles down to WebAssembly, the tool that you use will probably add in some code that will help. Add in some code to your .wasm file that will help make it easier. It'll do some of the stuff that the JS engine does for you. So it could ship down code for the encoding and decoding of bytes. Sometimes these tools even add more helpers and more APIs, language-specific ones, to make it simpler to interact with WebAssembly. And that code is called a runtime environment. So you can have a runtime environment that can make it easier to work with this memory. That's memory management in a nutshell. Now let's look at how this memory import is created and why it's created. I'm going to tip these mailboxes over on the side so that we can see JavaScript and WebAssembly working together. Now React's going to create a memory to pass in as an import. And all the JS engine is going to do internally is create an array buffer. So that's a JavaScript object that JS has a reference to, and JS allocates the memory for you. So you tell it how much memory you're going to need, and it will create an array buffer of that size. And if you need more memory later, you can do something called growing to make that array buffer larger. Handling WebAssembly's memory as an array buffer as an object in JavaScript does a few things for us. Because this is just a JavaScript object, that means that JavaScript can go and dig around in these bytes, as well as WebAssembly. And so in this way, WebAssembly and JavaScript can actually share memory and pass values back and forth. Instead of using a memory address, though, they're going to use array indices into that array buffer to do this. So for example, the WebAssembly module could put a string in memory, it would encode it into bytes, put it in there, and then it would tell JavaScript what index to use to access those bytes. So JavaScript can pull those bytes out and use them. And of course, most JavaScript doesn't know how to work directly with bytes. So you'll need something on the JavaScript side, like you have on the WebAssembly side, that can convert from bytes into a more useful data type, like a string. So in some browsers, you can use the text encoder and text decoder APIs, or a tool like Emscripten can add in JavaScript functions to do this. So that's the first benefit of WebAssembly's memory just being a JavaScript object. The WebAssembly and the JavaScript can pass values back and forth. A second benefit of this WebAssembly module just being a JavaScript object is that it prevents memory leaks. When the WebAssembly instance that it's attached to goes out of scope, then the engine knows it can just clear out this memory. It can just garbage collect. Finally, and most importantly, it provides memory isolation. So the bounds of the array provide a boundary, a limit to the memory that WebAssembly can directly interact with. It can directly touch all of the bytes that are inside of its memory, but it can't see anything that's outside of the bounds of that array. So for example, any other JavaScript objects like the window global, those aren't directly accessible from WebAssembly. And that's really important for security. When people hear that WebAssembly gives you direct access to memory, it can make them a little nervous because they think that a malicious WebAssembly module could go in and dig around in the bytes when it shouldn't be able to. But whenever there's a load or a store in WebAssembly, the engine does an array bounds check to make sure that the address is inside of WebAssembly's memory. And if it isn't, then the engine will throw an exception. So this will protect the rest of memory. So that is the memory import. The final type of import is related to security as well. It's called a table. Sometimes in a program, you want to be able to have a variable that points to a function. something like a callback that you can then pass around and into other functions. In C, these are called function pointers. The function lives in memory, and the variable, the function pointer, just points to that memory address. And if you need to later, you can point that to another function. So this should be a familiar concept. In web pages, all functions are just JavaScript objects. And because they're JavaScript objects, they live outside of WebAssembly's memory. Now, if we want to have a variable that points to one of these functions, we need to take the address, so that number, and we need to put it into our memory. But part of keeping web pages secure is keeping those memory addresses hidden. You don't want code in the web page to be able to see or manipulate that memory address, because if there is malicious code on the page, it can use that knowledge of where things are in memory to create an exploit. So for example, it could change this memory address that you have in there to point to a different memory location. And then when you try and call the function, instead of pulling up your function, it pulls up whatever code that attacker put in there. So that could be, maybe they embedded some malicious code in a string, and they knew exactly where to put it in memory. Tables make it possible to have function pointers, but in a way that isn't vulnerable to these kinds of attacks. A table is an array that lives outside of WebAssembly's memory, outside of the memory that WebAssembly has direct access to. And the values are references to functions, so they do actually expose those memory addresses in the array. But because it's not inside of WebAssembly's memory, WebAssembly can't actually see those. It does have access to the array indices, though. If the WebAssembly module wants to call one of these functions, it passes the index to an operation called call_indirect, and that will call the function for you. So right now, the use cases for tables is pretty limited. They were added to the spec specifically for this function pointer use case because C and C++ make a lot of use of function pointers. Because of this, the only references you can put in tables right now are function references. But as the capabilities of WebAssembly expand, for example, as there is direct access to the DOM, you're likely going to see other kinds of references being put in these tables. So those are the different kinds of imports that you can equip your instance with: values, function imports, memory, and tables. And your instance is now fully equipped and ready to go. So it has its instruction manual, which is the compiled code, and it also has all of its imports. Now the promise that we got when we called WebAssembly.instantiate can be resolved. We have the instance of the WebAssembly module, and now we can get down to the business of actually rendering. The kickoff of the rendering process will still look like it does today. You're going to call react-dom.render, and you're going to pass in an element and the container to put your React app in. And these are just JavaScript objects, so they live outside of WebAssembly's memory. React-dom.render is still a JavaScript function, but inside of this JavaScript function, it's going to pass off control to WebAssembly, which is going to build out the fiber tree. And if you want to learn more about how the fiber tree works, there's a talk after lunch, and also I gave a talk at ReactConf this year about that. We need to create an instance for this element. And because these two objects live in JavaScript memory, WebAssembly doesn't have direct access to them for now. We're going to need a way to call functions on them and access the properties. And this is where those function imports come in. So we'll have equipped our WebAssembly instance with JavaScript functions that do work on these JavaScript objects. We'll have a function import that knows how to create a React instance from an element. And this function import, as part of its closure, will also have access to an array that we start with the first element. And this will hold all of our elements as we build out. And we'll also have an array to hold the instances as we create them. So now to actually create an instance for this first element, the WebAssembly module will call the JavaScript function and will pass in 0, which is going to be the index of that root element. So the function would create the instance and add that to the array of instances. And then it's going to return the integer that is the index for that. So let's jump ahead a little bit to where we're going to call render on that. What WebAssembly would do is pass the index of the instance into another function import that will call render on that instance to create the elements, and then it'll add those to the elements array. And then it'll return an array of indices for those elements. Now, as this WebAssembly module goes along, as it creates instances, it's going to be creating the corresponding fibers, but it's going to be creating those in its own memory. So the fiber data structure is actually designed so that it could be used in a language like C. It has a fixed set of fields on it, and those fields are predictable in their size, so it's easy to allocate them. And most of these fields are easy to represent in WebAssembly's memory. So there are references to other fibers like child, sibling, and return, which are just addresses, or they're enumerables, which are easy to represent as numbers. For those fields which need to point to JavaScript objects, like state node, which points to the instance, we can use the array indices. So this WebAssembly module will build out the fiber tree this way, and then would pass control back to JavaScript, which would make the changes to the DOM. So what does this do for React? As we talked about before, it does help with code reuse, because it's written in C, you can share it with React Native where it can easily be compiled down. But will this help with the performance of React applications in the browser? The truth is that the short-term immediate impact of this on performance isn't clear. So let's break it down and see why. Here's a diagram that shows the kind of work that the JS engine would typically do for a web app. For each category, let's look at the potential for performance improvement. Decoding WebAssembly is faster than parsing JavaScript, which could potentially help, but we're not actually rewriting a huge part of the app here. Compiling and optimizing WebAssembly is also faster than JavaScript, but then again, since most of the code will still be JS, we won't see as large an improvement here as we would otherwise. Re-optimizing is something that the JS engine has to do sometimes, but in an application or a framework like React, you probably don't have much re-optimization going on because there are performance-focused devs working on it that understand JS engine internals and the tricks that you need to use to optimize for them. Then there's execution of the code. WebAssembly instructions can be anywhere between 10% and 800% faster than JavaScript, the equivalent JavaScript. But the operations in React are likely to be on the lower end of that range. And finally, there's garbage collection. There'll probably be some savings in garbage collection, but not as much as you'd think. And that's because a lot of the garbage that's created in React is React elements. And because a new set of those is created on each render. And for now, those elements live in JavaScript. Unless we can move things like those elements in the instances into WebAssembly's memory, we won't see much savings there. So you may be wondering why I said there's a question of whether or not it would be faster, because in each of these categories I've said there should be at least a little bit of a performance improvement. The reason it's a question is because doing what I've described introduces a little bit of overhead. So first off, we have to add a little bit of code to the two files that we wouldn't need if we were working just with JavaScript. For example, the code we need for encoding and decoding bytes in JavaScript, and the code that we need to do the same in WebAssembly, and the additional code also that we need of the runtime environment in that WebAssembly file. Now, sometimes people get confused because they think when we're talking about runtime environments that you need to include a huge runtime, and that's not actually true. You can pare down the runtime that you include in your WebAssembly file to just exactly the functions that you need, but we're probably going to need at least a little bit of the runtime. Additionally, there's a little bit of a cost for the calls, from JavaScript to WebAssembly and from WebAssembly to JavaScript. And this is just an issue for the time being. There's nothing inherent to calling WebAssembly code from JavaScript that makes it slow. It's just that browsers in the current JS engines, this hasn't been optimized yet. So for example, in Firefox right now, if you're making a call from JavaScript to WebAssembly, it has to go through a setup function. And that slows things down slightly when you make the first call. And we're only talking nanoseconds here. But if you're calling it from JavaScript into WebAssembly a lot, that can add up. Now, when you're calling the other way, when you're calling from WebAssembly to JavaScript in Firefox, it's actually pretty fast. But it's not as fast as it could be. It's not as fast as fully optimized JavaScript to JavaScript calls. So right now, if you have a lot of communication between JavaScript and WebAssembly, the overhead can add up. But as the engines optimize this away and bring these function calls up to speed, that overhead is going to be less and less of a problem. With all this in mind, the short-term performance impact of doing something like I described before, where you convert the reconciler to WebAssembly, is probably either a wash or a modest improvement. So that's in the short term. That's like in the next 3 to 6 months. But if you look a little bit longer term, if you think about what it could mean in a year or two from now, that's a different story. So everything I'm talking about from here on out is not what's in the browser, not what's in WebAssembly today, and not what's part of what tools we have today in the React ecosystem, but instead, it's what's coming in WebAssembly, or what tools we could potentially build. One of the things that was slow in the approach I just described was interacting with instances and elements, which are JavaScript objects. And part of that cost goes away once the engines are optimized. But even once that happens, there are some performance opportunities that we can't tap as long as elements and instances are in JavaScript. For example, they live in JavaScript memory, so JavaScript has to spend time keeping track of them and garbage collecting them. And that cost is going to be there unless we can start moving these things into WebAssembly's memory. But that means having the component code in WebAssembly memory. In WebAssembly, in a language that compiles to WebAssembly. And we already said that we don't want component authors to have to write in a language that compiles to WebAssembly. That's what I asserted before, and I think that a lot of you probably agree with that. But I want to take a step back. I want to look at the assumptions behind that assertion. So one of the assumptions is that JavaScript is easier to write, and in a lot of ways it is, because you don't need to learn about types or a compiler before you can start coding JavaScript. The early part of the learning curve for a language that compiles to WebAssembly like Rust probably looks something like this, whereas the same part of the learning curve for JavaScript probably looks more like this. But as the performance requirements for your app increase, I'd say that the learning curves start looking more like that. And that's because it's actually kind of hard to optimize JavaScript. You need to know a lot about JavaScript engine internals, and those internals are changing. It would be nice if we could have the advantages of JavaScript. So the speed that you can prototype and the speed with which you can learn how to write JavaScript, but also have the predictable performance of something like Rust when you're actually running the code. So I want to throw a what if out there. What if we could write some of our components in JavaScript and then have other ones in WebAssembly and run those side by side? Now, I don't want to imply that this is easy. Making languages interoperate like this is a known hard problem. But with the boundaries the way that they are in React and the way that components are decoupled from each other, there's a chance it's possible. And this could open up some really interesting workflows. Like you could prototype a whole bunch of components in JavaScript and then profile to see where your pain points are. Then just do those in WebAssembly. And other people have ideas for how to make this even easier, how to make tooling that makes it easy to have all of your components in WebAssembly. Now, if we have those kinds of tools and you can turn all of them into WebAssembly, you could see savings from parse and compile being faster. And you could also see improvements in garbage collection. But even without that tooling, if React makes it possible to have some of your components written in WebAssembly, then you could get rid of a lot of that optimization and re-optimization for components that are hard to optimize in JavaScript if you aren't a performance expert. So that's one place where changes to React itself and changes in the tooling ecosystem might open up new possibilities. There are also additions coming in WebAssembly that could lead to big wins. The first of these is support for threading. That will open up the possibility for parallelizing the reconciliation algorithm. Now, running work in parallel can make it go faster, and that statement may seem self-evident. But running work in parallel doesn't always make things faster. In fact, the React core team actually ran some experiments around this about a year or a year and a half ago with the tools that were available at that time. And they found that parallelizing the work would actually make things slower in a number of different use cases. Now, they were using web workers in JavaScript, and there are a couple of reasons why this isn't as fast as you might think. First off, the memory between different web workers is isolated, or at least it was at the time. So if you needed to share data between those web workers, you needed to send a message that had that data, which would then copy it into the other web worker's memory. It would be a lot faster if both of these web workers could work on the same memory at the same time. Now, since the React folks did this experiment, shared array buffers, which provide this kind of functionality, have become a reality. So if they were doing it today with the tools available today, they might actually have some different results. But shared array buffers don't make it possible to share JS objects, which are easy to operate on. Instead, you're just working with bytes, like we have in the WebAssembly memory. And multiple workers can touch those bytes at the same time, which means that you can have race conditions. And that makes working with shared array buffers pretty tricky. You really want to have a nice abstraction on top of this, and some tools have been added to JavaScript to help with these kinds of interactions. But really, this kind of shared memory concurrency is very new to JavaScript. With WebAssembly, you could choose a language like Rust, which has a focus on this kind of concurrency and gives you the right tools for the job. So shared array buffers help with the cost of sharing data between threads. Another cost of parallelizing is sharing the code between threads. And as I mentioned before, JavaScript objects are not shareable between web workers. Of course, the code that you're using, things like components or React, they're just objects. And this means that even though you've loaded the code in one web worker, it's not there in the other worker. You're still going to need to load it again in the other web worker, which includes compilation and optimization and re-optimization steps each time. But in WebAssembly, you actually have that compiled module. When you called webassembly.instantiate and it gave you back the instance, it also gives you back the compiled module. And that means that it's really easy to spin up new instances with this compiled code. So the support for threads that enable this kind of parallelization in WebAssembly is getting very close. Another thing that is likely to come in WebAssembly kind of soon is direct access to the DOM. And so I was talking about this before. It's because we don't have this direct access to the DOM that we need to pass in those functions to the WebAssembly module so that they can interact with the DOM using those functions. But once you have direct access to the DOM from WebAssembly, those functions aren't needed to call methods on the DOM. And at that point, there are fewer barriers to actually converting all of React, including the event system and renderers, to WebAssembly. Another thing that's on the horizon is integration with the browser's built-in garbage collection. Right now, if you want to run a garbage collected language, you can ship down your own GC as part of the .wasm file, and that will run side by side with the browser's GC, but that's not easy to get right for a number of different reasons. Once there's integration with the built-in GC, then WebAssembly compiled languages will be able to use that. So this could mean big things for languages like Elm or maybe OCaml and Reason. That's about all that I have time to cover in this talk. But I want to make clear that these are just a few of the ideas that people are talking about. People are also talking about ideas like incorporating a bytecode interpreter like what you see in Glimmer in React. And that would change what WebAssembly in React would look like. So I can't tell you exactly what WebAssembly means for React, but I hope that this talk has given you an idea of what maybe it could. Thank you again to everyone who talked through these ideas with me, especially to Luke and Sebastian, and thank you all for listening.